Today I'd like to tell you about a system that a group of us at Sentient Technologies built, and we like to call it visual product discovery. So let me start by showing you this screenshot of what happens when a user engages with the system. The first thing the user sees is a screen full of products. And the user is invited to click on the product that's most similar to what they want to buy. So for example, they might click on the boot shown there. After they click on the product, then they're given two options. They can either get more information about that product, which will lead to an option to buy it, and they'll also get another screen full of products. So this new screen full of products is enriched for products that are similar to the product that they clicked on in different respects. So in this case, there are more brown boots, there are more boots with buckles, there are more boots with this sort of intermediate size heel, more boots that are sort of mid-height, and other things. So after that, they might click on one of those products, and if they do, they'll get another pair of options. They, again, could buy the product, or they could, again, click on one member of the new screen full of products. And again, this new screen full of products is, again, enriched for products that have properties in common with now the two clicks that they made, and they're different from things that they didn't click on. So why is this helpful to shoppers, potentially? Because it can be hard to describe exactly what you want using words. You know, to try to list all of the properties of the product that you want could be impossible. And you know, some of the most important properties are impossible to put to words. They have to do with the feel of the product. It's easier to express preferences, and you know, it's even kind of fun. So at the core of our approach to designing a system like this is a deep neural network that transforms the original raw representation of the image to an embedding, which can be interpreted as describing, properties of the product that are more, coarse-grained, that have to do with shopping preferences, things like the appearance of buckles and height of the shoe and color and stuff like that. So here's a schematic diagram. The embeddings that we produce are 128 dimensional, but I've done a plot as if they were two-dimensional. So when you start off with the catalog, and now you apply this transformation to the images in the catalog, now we have a point in some space for each item in the catalog. And so now what I'd like to do is just walk you through a session of a user, a sample session of the user, now from the point of view of these embeddings in the catalog, right? So the first thing the system does is it chooses the items for the first screen, and the goal there is to represent the contents of the catalog, right? We want to show a diverse set of products so that, no matter what the user wants, there's something in that front screen that's representative of that type of thing. Then after the user selects an image, the next thing to do is to assign scores to products that reflect how likely we think it is that the user will be interested in that product after receiving this information that they prefer the object that they clicked on. So we have only a very small amount of information about their preferences, but we do know something. So after that, then we have found it helpful to select a list of the highest scoring, in this case boots, but in general products, and then choose a new screen from among those highest scoring products now to represent the context of this, represent the contents of this smaller collection of products. And then the user might click on that. We assign scores based on those new clicks, and so on. So to fill in the details of the design of a system like this, we have to work out how to design three key modules. First, we need to figure out how we're going to train those embeddings, the mappings from the raw images to the high-level representations. We have to decide how to score products, and then we have to decide how to choose the members of a screen of the highest from among the products with the highest scores. So our approach to all of these modules is based on the following idealized user model. So it refers to a particular member of the catalog that we call the target. So one way to think of this member of the catalog is that it is the ideal product in the catalog for the user at the point in time that the user has engaged with the system. Now, so the user may buy other elements of the catalog, but this is the one that the user would like the most. So then our model of the behavior of the user is a little bit like saying that given a screen full of products, the user will pick the products that is most similar to their target, to their ideal. But it's probabilistic. So they, if there are two products in the catalog that are roughly equally similar to the target, then it's roughly equally likely that the user will click on either one of those. And specifically, we take the soft min of the distance between the embedding for the target and the embedding for the member of the screen. So we borrow this use of the soft min for a model like this from earlier work. And in this formula, this phi function is the function that maps from the raw representation of the product to the embedding. So now that we have this user model, there's a very natural way to approach training the deep network that maps the raw representations to the embeddings. When we do this training, we have examples that mimic individual interactions between the user and the system. So there's an example for each triple consisting of a target, a screen, and then a user choice. And what we optimize is the probability of generating the user's behaviors under the model. As we choose the mapping from inputs to representations, that if we use that mapping, we would have been most likely to see the click behaviors that we did. And we do that in a standard way using stochastic gradient descent, that is making updates one example at a time, and we regularize using common techniques. And we got the code for this by starting with code provided by Hofer and Eilon for a similarity learning neural network based on a different criterion, and we just modified the criterion. So now we have a criterion. We still need to decide how we're going to get training data. So our approach for the first model, and we've since extended it, was to generate our training data in two passes. First, we generated a preliminary mapping, and then we refined it. So the preliminary mapping was done by just generating random targets from the catalog and random screens, completely uniformly at random from the catalog, and giving those to Mechanical Turk judges, and asking the judges which item of this set of products, in this case it would be like a simulated screen, is most similar to the target. Okay, so the trouble with that kind of training data is that most pairs of items from a given catalog are quite different from one another. And so when a system is being trained with this data, it's not being challenged to make fine-grained distinctions between products. Whereas when it's used in the field, as the user searches, the products will be getting more and more similar to one another, and also more and more similar to what they want. And so it will be necessary to make fine-grained distinctions between products later on in the process. And so the way we approach generating data with that property is to use our original embedding, the embedding that we generated using the rough data, to build a system by filling in the other modules in a way that I'll describe later. And then we simulated the user using our probability model. So we would have the whole system. The system would generate a screen. And then we would ask, what would the user do if the user saw this screen? Well, we'd use the probability model that we got from the first pass and generate an artificial click, with a probability governed by that preliminary model. So in this way now, we get the simulated data where the system does zoom in on the target, and so now we have data where there are a lot of similar products that have to be distinguished. So then we take those target screen pairs, and then we ask judges again which of these items is most similar to the target, and now they have to make finer distinctions. Okay, so I've told you about training the embeddings. Next, I'd like to talk about scoring the products. So remember, the problem here is now we've seen the user presented with a number of opportunities to choose members of screens that are most similar to what they want. And we want to estimate now what it is that the user wants. So our approach here is to use as a score the probability that a given product is the target. And we can evaluate those probabilities by using Bayes' rule, right? So the probability that a product is the target, right, is a simple function of the probability that you'd see the behaviors that you did given that it was the target. And we can break that down into one for each interaction. You know, what's the probability you would have seen that click given that this was the target? And we have our user model. That gives us those probabilities. So the other part of the formula for the probability that a given product is the target is its prior probability. What was the probability that it was the target before we had seen anything from the user? So our original approach to that was just to regard all of the products as being equally likely. But this is a handle that can be provided to clients for the product, for example, to promote certain goods, or you could use this, for example, to make your system sensitive to the geolocation of the person engaging with the system, or that sort of thing. So this Bayesian approach to assigning scores to things that are being searched for was also borrowed from earlier work. So the last thing I want to talk about is selecting screens. Now we've got the scores. We think we know what the user is more or less likely to be interested in. Now, how are we going to choose products to show to the user? So the issue here is that when you're making this choice, there are two competing goals. We want to provide the user with the opportunity to tell us more about their interests, right? Because after just one click, we know very little about what they're interested in. But at the same time, we want to give the merchant a chance to make a sale. So we want to enrich the screen for items that are likely to be interesting to the user now, right? So we want to set ourselves up for future success, but also take a shot at being successful. So this is an instance of a more general phenomenon. As many of you know, this exploration-exploitation trade-off, and there are off-the-shelf techniques that can be applied. And so we borrowed one that's called Thompson Sampling. So in this context, it seems that Thompson Sampling is it requires one, or prescribes choosing a screen in the following way. You repeatedly randomly choose a product and add it to the screen. The probability that you add a product to the screen is the posterior probability that that product is the target. So we've calculated, or you sample with probability proportional to the scores. And you keep doing that until you have a screen full of products. So this is going to be enriched for promising products, right? So for example, suppose there's only one product that had that was overwhelmingly likely to be of interest to the user. That would definitely be there in the screen. But if you had a subset of the catalog, right, that was still alive as being of interest to the user, but the members of that subset were roughly equally likely to be of interest, then you would be sampling from that subset, right, and excluding the stuff that you have eliminated as candidates. And as a result of that aspect of the behavior, it maintains some diversity, right? You sort of represent what's left, what's still alive, given what we know about the user after the first few clicks. And this practice has some theoretical support in other contexts, but it seems to trade appropriately, but with some caveats. So a second approach that we also evaluated and that's implemented and available, but that's not being used in production now, is to choose the screen to minimize an objective function. The objective function tries to capture the notion that we represent that portion of the catalog that's still alive. So the criterion is a sum over all the products in the catalog. And for each term having to do with a given product, there are two factors. So the first factor has to do with how well this product is approximated in the screen. And it's just the distance of the closest member of the screen to that product, what you would have in a usual k-means objective function if it were squared. And the second is, the other factor is the importance of approximating that product, right? So it's the probability that that product is the target, right? And so one way to think of this is a sort of a softening or a relaxation of a criterion that says, let's approximate everything that's still alive as being of interest to the user, using a usual criterion for the fidelity of approximation of a sort of discrete subset of a bigger set. So here's a bit of a hack that we could not eliminate from the system. It's what you might call it candidate reduction, and we use it for both of the methods for choosing screens. So what we do is before we apply these methods, which might be regarded as being principled, we take the original catalog and we remove all the lowest scoring items from the catalog and apply whichever technique to the items that are left. So the fraction of the catalog that is kept reduces as the number of iterations of interactions continues, and doing this helped according to the ways that we have for evaluating methods. From the point of view of an exploration-exploitation trade-off, this is tilting the balance more toward exploitation. So we have evaluated methods in a few different ways. One is we devised a find the boot game, which we ask Mechanical Turk judges and judges employed by other companies to play. So there we show the judge the target and we ask them which member of the screen is closest to the target, but then they iterate again. We generate a new screen and then we ask them which item of the new screen is closest to the target, and we use our system iteratively as if it were being used in the field. And then we can evaluate a proxy for how long it would take a user to find something to buy. So we have other evaluation metrics that examine things offline, and maybe I'll skip those. And of course, A/B test with the production system would be the ultimate gold standard. So I don't have time to present detailed results, but I'll just say this candidate selection, like we don't like to do it, but we can't get rid of it because it seems that it really helps. And the other take-home message is that this Thompson sampling, which runs much faster than the K-metoids approach, performs just as well with respect to these click the targets metrics. So are there any questions or comments?
Two questions. The first one is the Turkers that you used. Did you have any pre-qualification tests for them?
No, but we did do some, not that I know of, but we did do some evaluation afterwards.
So if you did, how did you correct for country, region of country, gender, age?
We didn't.
You may be representing what the world wants in a boot, but on the West Coast or on the East Coast, for a woman who's 35, that click probability is like totally off, right?
I think you're totally right about that. Oh, yes, sorry. So the question was, did you have any pre-qualification tests for the Turkers? And the answer was no. And then the question was, well, these Turkers may have different preferences on average than clients for your system. Is that a fair representation of your point? And I agree. We do also use a company called Spare5 that gives us users who are shoppers and have characteristics that are more like what we expect the shoppers will be, but they're more expensive. So, yeah, good point. Yes, please.
I had a question about how many products do you have in the catalog you're working with, and what was the kind of competition on the legs of the performance? Like, I can see you've got at least one approximate technique, and like how fast can you go between questions?
Yeah. Yes, thank you. So the question was, how big of a catalog are we handling, and how fast can we produce the next screen for that size of catalog? And I guess generally, these type of complexity issues. So we have been handling catalogs of different sizes for different clients. I think the thing that I talked about here, a few thousand. Some of them had more like tens of thousands, and we produce the new screens in I don't know, a handful of milliseconds, like maybe 10 or 20, and it does it motivated using Thompson sampling instead of this K-metoids type thing. Although the K-metoids, it did well enough, but the Thompson sampling was a lot faster. We have designed and implemented techniques that scale to much bigger catalogs. When we do that, we can't calculate all of these probabilities, right? And so we on the fly sort of do, I mean, I'll just say very vaguely, you know, sort of a Markov chain Monte Carlo thing where we're on the fly calculating probabilities for some of the members of the catalog in such a way that we can sample from an approximation to the posterior without ever calculating all those probabilities. And so, yeah, that's not in production yet because we haven't had a client with a big enough catalog yet, but we're ready for that when it comes.